Hello, and welcome to our talk at the 12th Annual Non-Volatile Memories Workshop. My name is Jessica Sinners, and I'm a PhD student at Duke University.
My name is Xinyu, and I'm a junior undergraduate student at Duke.
And together with Ahmed Hareedy and Robert Calderbank, we're here to share with you the results of our research on calculating the power spectra of constrained codes typically associated with level-based signaling. Real quick, we wanted to start our talk with a short summary slide of the motivation and results in our work to let you know what you'll be hearing from us today. To begin, we wanted to stress the importance of the constrained codes that we're looking at. They find application not only in data storage devices such as magnetic recording and flash memory, but others. And constrained codes in general can find application in things such as barcodes. Our research looks at calculating the power spectra density, or PSD for short, for constrained codes. Making PSD calculations efficient and simple for codes of interest allows system designers to more easily compare and ultimately choose a particular coding scheme for their given application by allowing them to understand how power is distributed across frequencies for each code. An example of this can be seen in the applications of optical recording and communication over transmission lines. It is required in these applications that the code be DC-free. So using the power spectra density to view whether or not there is discrete power at 0 hertz is a simple way to verify whether or not that constraint is met. Even more so, the width of the dip in the PSD around 0 hertz can be considered. The results of our research include power spectra density calculations for finite length constrained codes with level-based signaling whose primary applications are in magnetic recording and flash. Finite length constrained codes are more practical, and so they were a primary focus for us. Additionally, their PSD calculations are a bit more complicated, as you'll see later, even though they are more desirable to obtain. It is also true that experimentally determining the PSD for finite length codes through Monte Carlo simulations simply isn't an efficient solution. So here we're going to list our three main contributions. First, we describe a method for calculating the PSD of any level-based constrained code that can be modeled by an FSTD. Secondly, we provide a closed-form solution for calculating the power spectra density of codes constrained by the separation of bit transitions. In the finite length realm, these are going to be codes like A-loco and loco codes. And then thirdly, we want to highlight that all of our theoretical results match perfectly with our experimental results. The experimental results are simply Monte Carlo simulation results. So here in the two pictures shown, you can see examples from the A-loco and loco coding families where we have our theoretical and our experimental results matching perfectly. For a brief history on constrained codes, we begin with Shannon introducing codes for constrained channels in 1948. He showed that an FSTD can generate all constrained sequences and that the eigenvalues of the FSTD can then be used to calculate the channel's capacity. Then in the 1980s, RLL codes began being used in magnetic recording devices to improve peak detection, even though RLL was technically invented in 1972. RLL codes control the minimum and maximum separation between transitions in a signal and are therefore typically associated with transition-based signaling rather than level-based signaling. Jumping ahead to now, constrained codes find application in many systems. For example, they're in magnetic recording systems where we've adopted sequence detection. It's also in low-resolution media where you want to prevent short pulses from occurring. We also use them in flash memory, where we want to avoid high-low-high charge levels on adjacent cells to avoid errors. Additionally, they help minimize errors in communication over transmission lines. In this talk, I have so far mentioned transition and level-based signaling. So here I'd like to compare the two. Transition-based signaling, such as bipolar non-return to zero inverted signaling, or NRZI for short, is signaling where if you've got a bit 0, you would associate that with no transition in the signal. If you have a bit 1, that would be a transition. So you can see on the top line of our figure here that every time there's a 1, we're going to transition to the next level, or to the opposite level, I guess. And then every time we have a 0, we're going to hold at the current level we're at. For level-based signaling, we use bipolar non-return to zero signaling, or NRZ for short, And in this case, if the bit is a 0, we're going to put the signal at a level -1. And if the bit is a 1, we're going to go to the +1 level. Again, we focus on the level-based signaling codes. In the infinite length realm, these are going to be AX constrained and SX constrained. And in the finite length realm, we focus on ALOCO and LOCO codes. And all 4 of these will have formal definitions pop up later in this presentation. Going forward, I would like to make you aware of a few assumptions that we have. So first of all, we assume that symbol length T is equal to 1, so that all the frequencies we plot against are considered normalized. Additionally, when we say theoretical results, that simply means that these results were calculated using our methods. And then if we have experimental results, those are simply going to be Monte Carlo results.
So in data storage and transmission, deriving the power spectrum density of a random stream of data is critical in both the infinite and, more importantly, the finite length scenarios. So how the power is distributed across different frequencies can reveal key properties that prove useful in choosing an appropriate code for an application of interest. So if we have a glimpse at some of our PSD plots, we can identify properties such as the stream bandwidth, which is the frequency range in which most of the power is allocated, and the average power of the stream at DC, as well as other frequencies with discrete power. So the motivation of our research is the desire to be able to provide system designers with a method for analyzing these sort of spectrum properties for various level-based codes. And consider this example alone, this spectrum analysis could allow for channel signal to noise ratio calculations more easily be done at various frequencies. And like this example, we will focus on codes constrained by the separation of their transitions, like the local and alocal. And throughout, we denote the PSD of a code sequence xn as S sub x of n of d, which is the Fourier transform of its autocorrelation function Rx of k, where k is a time lag and d is some complex exponential for some frequency f and time interval t that we take to be 1. And in addition, if xn is cyclostationary with non-zero mean, then we can observe those kind of discrete power components. This will be discussed more later. The method we derive for calculating a code's PSD with respect to level-based signaling actually involves 2 steps. And the first step is to derive the code's one-state transition matrix, aka OSTM, based on its FSTD. And the FSTD will generate a valid sequence xn that satisfies the constraints. Each edge is in the FSTD is labeled by a single symbol, either 0 or 1. And that generates the next state. And we have to make sure that all the incoming edges for a given state are generated by the same symbol. We also keep track of the probabilities of each transition. And then we derive the one-step state transition diagram, or STD, of the same system by assigning states only to the vertices where the most recent generated bit is a 1. And edges of the OSTD are labeled by the number of transitions it takes to get from one OSTD state to the next OSTD state according to the FSTD. So this way, you can define the sequence produced by the OSTD as TI, and each TI just represents the number of consecutive zeros along with the ending 1 of the i's run in xn. We also keep track of the probabilities associated with these edges in OSTD. And finally, the one-state transition matrix, GFD, has entries being a summation over all corresponding edges in the OSTD. So Pij of T here is the probability of transitioning from state I to state J, and T here is just the random length that characterizes this transition. So we here give an example of deriving the OSTD based on the FSTD for A1 constraint code. So we'll give a full definition of AX constraint codes later. For now, we just need to know that the example has only one forbidden pattern, and that is 101. So we'll begin with the FSTD that forbids this pattern 101 and keep tracks of the transition probabilities. So we can see that all the incoming edges in FSTD for a given state are generated by the same symbol. And moreover, for state 0, 1, and 1, 1, all their incoming edges are 1. So we'll label them as F1 and F2, which are the only two states in the OSTD. And then we can shrink this FSTD into the OSTD and label each OSTD edge by the number of FSTD transitions it takes. So for example, the self loop at F1 just are the same with the self loop from 0, 1 to 0, 1 itself in FSTD, not self loop, the pass. And we can see that the passes can have lengths of 3. Or if we take more self loops at 0, 0, which probability of 1 over 2, we will have pass lengths of 4, 5, to infinity. And the corresponding probabilities will be 1 over 4, 1 over 8, also to getting smaller and smaller. So this results in the alpha term in the OSTM GFD matrix, where alpha is an infinite sum of, after calculating the OSTD and the probabilities in the OSTD. Our signal generation scheme is shown at the top as a second step. As mentioned, we're concerning with level-based signaling in this research, so we apply NRZ signaling to the code sequence exon. And additionally, we assume simple rectangular pulse shaping, which leads us to the right signal WFD. We also put the detailed formula of this realization here. And remember, GFD is the OSTM we generate in our first step based on the code's FFT. And this term, along with the stationary distribution and equilibrium probability, are used to calculate the PSD of Xn. Though the right signal, WFD, is often the signal of our interest, if the application we're considering utilize the discrete signal either prior to or after signaling, and then our method can also be used to calculate the PSD of the intermediate signals Xn and Yn. As an example of this would be using the PSD of Xn to evaluate the spectral properties of the readout signal in solid state media. So we here present the full definition and general results of AX constraint code, which prevent patterns in the asymmetric set of 101, 1001, where ones only appear at the two ends. So we prevent these patterns from occurring in the infinite length sequence. We can see the OSTM of general constraint AX constraint codes here. GFD is sparse for large X because there's a scaled identity matrix making up the majority of GFD. X here is the number of consecutive zeros between the two ones in the set of AX. After applying the formula on the previous slide, our method matched perfectly with the Monte Carlo result, and we can even see the expected peak at DC due to the asymmetry of AX constraint code. And this is actually a discrete value that can be calculated out with our method, which is x squared over x plus 4 squared. And then we also want to show you the definition of the symmetric SX constraint codes and their general results. So in addition to the forbidden patterns of 101 in AX constraint codes, SX also forbids 010, 0110, where zeros only appear at the two ends in the infinite sequence. So this makes this SX constraint code symmetric. And here's the OSTM GFD of SX, and it is even more sparse for large X than AX constraint code was. So same with the previous plot, our method matched perfectly with the Monte Carlo result, and we can clearly see the absence of discrete DC power due to the symmetry of SX constraint codes.
So in practical systems, as mentioned, we usually care about the finite length codes. To calculate their power spectral densities, we first provide a method for generating the finite state transition diagram. So first, we assume that all code words are equal probable. Then we define a grid of states for the finite state transition diagram, where each column is going to correspond to a bit position within the code word or its bridging pattern. And then we're going to have the rows correspond to a specific pattern of the previous symbols. An example is about to be provided. So if that's confusing, that's okay. To define bridging, these are just bits that are going to appear between code words so that we don't have any of the forbidden patterns happening between code word transitions. Here's that example. So consider the arbitrary code book C here, where we've got 4 different code words that I've got listed, and we're just going to use simple 0 bridging between every single code word. So here I've got a grid of states that's 4 by 4. And like I said, the columns are corresponding to a bit position within its code word and bridging pattern. So since the code words are 3 in length, we've got 3 plus the 1 length of bridging, which is just 1. So we've got four columns here. And then if you look at these code words specifically, you'll notice that what bit comes next only depends on the previous 2 bits, well, 1 bit plus itself. And so you've got 2 to the 2 possible patterns. And so you're going to get 4 rows here, which we've got demonstrated. And so if you want to follow perhaps 1, 1, 0 throughout this finite state transition diagram, you would start at this FSTD state right here. And then you would go, okay, so this is a 1, we're going to go to 1 and then 0, and then we bridge with 0. And now we're back here at either a 1 or 0 starting state. And so then, since we've noticed that this finite state transition diagram has some unused states, we just delete those, and we end up with this as our resulting FSTD. It will be seen later in examples that sometimes you can also combine states that have the same leaving edges and the same probabilities on those leaving edges. Okay, so we first provide the definitions of aloco and loco codes because these are the codes of interest. And so aloco here is listed at the top. Its primary application is in flash memory. And so it's denoted as AC sub m of x, where m and x are parameters of the code. And it simply stands for asymmetric lexicographically ordered constrained codes. So these are codes that include all the code words that are m in length, and then binary, and also ordered lexicographically, and forbid all the patterns from the exact same set we saw in AX constrained codes. And though this definition does require that the code words be ordered lexicographically, that's actually not a constraint that is needed to follow our power spectral density calculations. And so typically aloco bridging patterns are 0 to the x unless the previous code word ends in a 1 and the next code word begins in a 1. Then we're going to use 1 to the x. And so that just means that if x for, if aloco and x equals 1, then you're going to have just a 0 in between every code word and its next one, unless you fit the constraint I just mentioned, then it's just going to be 1. And then loco codes are very similar to aloco, except for they're the symmetric version. And their typical application is in magnetic recording. And so you can see here that instead of forbidding patterns from AX, we're now going to forbid patterns from XX, which you also saw the definition of previously. And the bridging pattern that loco typically uses is Z to the X bridging, where Z is a no transmission symbol. And so as we mentioned with our inner Z signaling, we've got a -1 and a +1 level. And so all this is going to mean is that there's no right there. So it's going to be at 0. And so now loco is a 3-level signaling scheme. And so for both loco and aloco, we've got a little table here kind of demonstrating how our finite state transition grid of states is generated based on what I just showed you in the last slide. So the parameter m again describes the code word length, and then you can also see from their bridging schemes that the bridging length is x for both aloco and loco. So the number of columns is going to be m plus x. And then it just turns out that the length of the largest error, which is defined by the sets AX and SX, is going to be x plus 2 bits long. And so since we consider the previous bits and we don't count the current bit, we're going to be at 2 to the x plus 1 number of rows. And so in the end, the OSTM that we calculate using that finite state transition diagram is at maximum going to be size m plus x times 2 to the x. And since it's a square matrix, it's going to be that in the other dimension too. And so kind of key to note here is that since m is the length of the code word, if you end up going to really large length code word sets, you're going to find that this matrix is at maximum going to linearly increase with that, which ends up being very efficient in calculations, especially if you're using software. Okay. Another interesting thing about finite length codes is that they potentially possess high levels of cyclostationarity, which just means that they have periodic statistics. So it is well known that time synchronous pulse amplitude modulated signals are cyclostationary in general. And that period is going to be equal to t, or that symbol length. But it turns out for finite length codes that are of m length, we're going to see a higher level of cyclostationarity with the period equal to m plus whatever that length of the bridging pattern is. So this is the exact same dimension that is determining the number of columns in that grid of states that I mentioned in the finite state transition diagram slide. And so to account for this, our autocorrelation functions in calculation are going to be phase averaged. And so I've got right here the math demonstrating that. And so overall, if you do have this cyclostationarity that results in discrete components, if you've got a non-zero mean, then you're going to have two different components of your power spectral density. One's going to be continuous and one's going to be discrete, which we kind of showed in plots earlier already. And so I've kind of listed here just easily that the Fourier transform of an aperiodic portion of your autocorrelation function is going to correspond to the continuous part. And this is exactly what we're going to calculate with the method that we've described in this talk so far. And then if you want to calculate the discrete components, you actually just need to consider the periodic portion of your autocorrelation function and use Fourier analysis on that. Okay, so here's an example of A loco. We've got m equal to 4 and x equal to 1. We're using the traditional bridging scheme, which we've already gone over. And so you can see here in the code book that for this particular A loco code, we're not seeing any patterns of 1, 0, 1. And then we demonstrate the FSTD in this figure shown. And we've actually already labeled the states that are going to be used in the OSTD as F1, F2, F3, F4, and F5. And you can see that we do end up combining states in this example. And so we've got two F1s, and in the end, those are going to combine and make our OSTM smaller. So exactly what this OSTM looks like for a particular code is not necessarily the key thing of this talk. What's most important is that you can start to see patterns in this OSTM. So if you look at this diagonal here, you kind of see a pattern. If you look at this diagonal, there's a pattern, and you can see that the bottom row is pretty sparse and the last column's pretty sparse. And it turns out that the numbers associated with this pattern are only dependent on M, X, and then the cardinalities of the code book, whether that be the full cardinality or the cardinality of subsets of the code book. So here I've got the theoretical and experimental results for the power spectral density of the continuous component, which we calculated using our method, and they match perfectly. We also have the discrete components calculated out using Fourier analysis, and that would be useful for a system designer as well. Okay, so the general results of A loco, as we mentioned, there's a pattern to that OSTM, and it depends on M, X, and the cardinalities. And so we listed the general result in terms of these parameters. And so you can see here that there is a submatrix A that does have to follow a set of rules to find certain entries, but it all boils down to the fact that they're all dependent on these cardinalities in M and X. And that's really as simple as it is. They're just a set of instructions. And so then we went ahead and plotted for multiple X's and M's of A loco, the power spectral density. And you can see to the left an example of where many of these codes we saw, again, the experimental and the theoretical match perfectly. We also looked at loco codes. And because we mentioned earlier that loco is a 3-level signal, we actually had to take sort of a different approach in that we considered 3 subsignals and then combining the power spectral density of those 3 signals to get the final power spectral density of the full loco code with NRZ signaling. So the 3 signals we defined are A, B, and C, and the rules for exactly what those signals represent are kind of shown in the bullets here. And in the end, it turns out that the full power spectral density of loco codes, which is SY of D there, is going to, well, before right signal, I guess, is going to be a function of the subsignal A and subsignal C power spectral densities. And again, we find that for subsignal A in particular, we find a pattern like we did in A loco codes for the OSTM. And that OSTM is again going to be dependent on M, X, and the cardinality of the code book, which is great and easy to follow. And it's just a simple set of instructions. And so We plotted, again, the power spectral density of loco codes versus their experimental Monte Carlo results, and we matched them perfectly, which is wonderful. Okay, so you might be wondering, okay, you focused only on loco, aloco, AX constrained, and SX constrained, but what about other codes? What would you do? So first of all, we'd like to highlight that the method for calculating the power spectral density of a level-based code works for any binary code that can be modeled as a finite state transition diagram. And in fact, if it's not a two-level code like loco, there are ways to get around that and using subsignals to calculate the full power spectral density. So it's even more applicable. And then secondly, the method for deriving the finite state transition diagram, in which we define a grid of states, is useful for any binary code whose constraints only require considering a specific number of previous signals, which I've labeled here as K. And then in general, you can put a bound on the size of that OSTM in terms of K, as well as the length of the code word and its bridging L, which I've got listed here. It's very similar to the one you saw for aloco and loco. So we were also concerned about specifically clocked aloco and loco. These are codes, these are essentially just aloco and loco that don't have the full 0 and full 1 code words in them. And this allows for the receiver to retrieve the clock of the transmitter from the signal, which is often useful in practical systems. And so what we found is that now each transition doesn't necessarily depend on the previous x+1 bits like we saw with loco and aloco. Now, sometimes it depends on more bits because it requires knowledge of the full code word that it's currently in. And this can cause the OSTM to grow quite large. So what we recommend is using an algorithmic approach to calculate the OSTM. And we demonstrate this in our full paper. The particular algorithm we use is breadth first search. So in conclusion, highlighting our three main contributions again, we first describe a method for calculating the power spectral density of any level-based constraint code that can be modeled by a finite state transition diagram. And it's just a series of steps. First, we model it in the FSTD, then we model it as an OSTD, then we calculate the OSTM from that, and then we calculate the power spectral density from there. Secondly, we provided the closed form solution for a family of codes of interest, specifically an asymmetric set of codes, both in the finite length and the infinite length, that has particular application in flash memory. And then we also looked at the symmetric codes, SX constrained and loco, which have application in magnetic recording and communication over transmission lines. Then we demonstrate that our solutions match perfectly with Monte Carlo simulation results. So with that, we'd like to conclude our talk, and I'd like to highlight a few of our references here, specifically 3 and 4, if you want to learn a little bit more about loco and aloco codes. These are the papers that introduce those. And then also 6 was extremely useful to us in our research as the first contribution of ours of calculating the power spectral density of a level-based signaling associated code. They do for transition-based signaling, and it's a little different, but very similar and super useful to look at. And so thank you for attending our talk. Our contact information is below, and we hope you have a good rest of the conference. Thanks.